In the name of God, the most gracious, the most merciful. Praise be to God, and may blessings and peace be upon the messenger of God, our Master Muhammad, and upon all his family and companions. And now, by the declining day, indeed, mankind is in loss, except for those who have believed and done righteous deeds, and advised each other to truth, and advised each other to patience. We aim to explore adjusting the relationship between fault clearing time and fault current. Generally, this involves 4 steps: selecting the appropriate CT, choosing the operating value, selecting the suitable curve with CT values, and performing calculations. First, choose the right CT for the overcurrent relay. Consider 2 notes. The maximum load should produce a current in the CT secondary of around 1 amp if the CT ratio used. To adjust this, there are 4 steps. The steps start by selecting the right CT for this, then selecting the value it starts, followed by selecting the right curve with CT values, and finally, we calculate. The first step asks how to choose the right CT. To select the right CT, consider 2 notes. First, maximum load should produce 1 amp in CT secondary if CT ratio is 1 amp, or 5 amps if CT ratio is 5 amps. Choose the closest standard value above the normal current. Choosing the right CT for an overcurrent relay involves 2 key considerations. First, ensure the maximum load in normal conditions results in a CT secondary current of about 1 amp for a 1 amp CT ratio, or 5 amps for a 5 amp CT ratio. Select the nearest standard value above the normal current. Second, the maximum short circuit current during a fault should not cause CT saturation. To ensure this, choose the correct CT class. For instance, a CT with a 300.1 ratio and a 5B20 class maintains 5% accuracy up to 20 times the normal current. Beyond this, accuracy drops, indicating saturation. The expected max short circuit current should not saturate. How to ensure it won't saturate the CT? Select the right CT class. E.g., a CT with 300.1 ratio and 5B20 class keeps 5% accuracy up to 20 times normal current. Beyond 20 times, it loses 5% accuracy, indicating saturation. Calculate to ensure it's under 6,000 amps, 20 times 300. Exceeding 6,000 amps means CT saturates during a fault. This CT keeps accuracy within 5% and keeps accuracy up to 20x normal current. After 20x normal current, the CT will lose 5% accuracy, indicating saturation phase. Calculate value should be 6,000 amps, 26,300. If 6,000 amps, CT enters saturation during fault. If max short circuit current 6,000 amps, it is suitable, no saturation during fault. Summary: choose CT based on CT ratio and CT class. Next, adjust overcurrent relay by choosing suitable pickup current. If current exceeds 6,000 amps, CT saturates. If maximum short circuit current is under 6,000 amps, it's suitable. Choose CT based on CT ratio and class. If the value of the maximum short circuit current is less than 6,000 amps, which is 20 times the normal current, we say that it is suitable and will not experience saturation during a fault. So, in summary, the appropriate CT is chosen based on 2 factors. The first factor is selecting the right CT ratio, and the second factor is selecting the appropriate CT class. The second step in adjusting the overcurrent relay is to choose the suitable pickup current. So what are the principles for selecting this pickup current? Setting pickup is choosing a value above feeder rated current. If unknown, set above max load current, usually 125% to 150% more. Important, what differs rated from load current? Rated current is max continuous output without overheating as per design. Load current is actual drawn current. E.g., transformer provides 300 amps. Load needs 100 amps. 300 is rated, 100 is load current. If load draws 300 amps, it is full load current. It is the maximum current that comes out of the equipment continuously without a rise in its temperature, and it is mentioned in, and this equipment is usually designed for this current. As for it, it is the current actually drawn from this equipment. For example, we say that this transformer is capable of giving you 300 amperes, but the load only needs 100 amps. So we say that these 300 are the rated current, and these 100 amps actually drawn by the load are the load current. If the load draws the full 300 amps, then we say that it is full load current. We calculate the pickup current by increasing the maximum load current by 125%. to 150%. It's based on 100 amps. The pickup current setting is 125% of 100 amps, resulting in 125 amps. This ensures the relay doesn't operate incorrectly at maximum load. If the load increases to 150 amps, we recalculate the pickup current to 125% of 150 amps. Some suggest setting the pickup current based on rated current to avoid recalculating with each new load. Now, if the load current is 100 amps, what if we add a load in the future and the load current becomes 150 amps? What should we do? The solution is simple. If a new load is added in the future, we need to recalculate the pickup current based on the new load or the new maximum load current. So it would be 125% of the 150 amps, not the 100 amps, to ensure that the relay will not operate incorrectly when the maximum load current is present. The group that chose the pickup setting based on the rated current in amps rather than the maximum load current said every time we add a load, we would have to redo the calculations. They wanted to set the pickup current value fixed, so no matter how many loads are added in the future, the pickup current value remains fixed. They took 125% of the rated current value, which is 300 amps, not 100 amps, making it 375 amps. What if a fault occurs and the fault current does not reach 125% of the rated current? The relay won't detect it. The group calculating pickup value by max load asked the group using rated current, what if a fault occurs and the fault current does not reach 125% of the rated current? The relay won't detect the fault. E.g., if the fault current is 370 amps and the pickup current is set at 125% of the rated current, equal to 375 amps, the fault current is less than the setting value, so the relay won't see the fault, considering it an impedance fault. The value should be based on the rated current or detect lowest expected fault. The pickup current was set at 125% of the relay current, equal to 375 amps. The fault current is less than the setting value, so the relay won't see the fault, considering it an impedance fault. The value should be based on the rated or maximum load current. The pickup current must be less than this fault current. It should be less than 2/3 of the lowest fault current. Pickup current must be below the lowest fault current to detect all faults. E.g., if max load is 50 amps and M in short circuit is 250 amps, pickup should be 125% of 50 amps to 250 amps. The pickup current value should be less than the lowest expected fault current to ensure it can detect all different fault conditions. There is even a practical rule stating that the pickup current value should be less than 2/3 of the lowest possible fault current on the bus bar. For example, if the maximum load current is 50 amps and the minimum short circuit current is 250 amps, then the pickup setting current should be in the range of 125% of 50 amps up to 250 amps. Choosing any value between them would be appropriate. Someone might ask about the 250 amp. The minimum short circuit current is 250A, so the pickup setting current should be in the range of 125% of 50A up to 250A. Choosing any value between them would be appropriate. Someone might ask a question about the 250 amps. The 250 amps and choosing any value between them would be appropriate. And someone might ask a question, how can I know what the maximum expected fault current is and what the minimum expected fault current is? The maximum possible or expected fault current is the closest point that the relay can detect, meaning when the current seen by the relay is at its lowest, therefore, the minimum possible fault current is the farthest point that the relay can detect, where the impedance value is at its highest, which is usually at the end of the line. This is why it's called a line end fault. Both values can easily be summarized using programs like ETAB, EasyPower, or other similar software. It is important to note that the relay is required to open contacts in different situations, and it is not required to detect faults. At this stage, after we have determined the appropriate settings in the first step and then found the value, in the second step, we are now in the third step, where we will find the suitable time for a specific current. This is done by selecting the appropriate operating curve and then choosing the TMS value or the TDS value. We mentioned that the TMS value is referred to as one thing, while the TDS value is referred to as another. Both terms are synonymous, but each term follows its respective standard. As we discussed earlier, in order to select the TMS value correctly, we must consider the time coordination rules between different protection devices known as a coordination study. For example, if we assume that relay A will detect a fault and disconnect it within a time of 0.15 seconds, this means that relay B should disconnect the same fault after a longer time in case relay A fails to detect the fault for any reason. In most cases, a time period is set called the time gap or relay time grading margin, which serves as a time buffer between the two relays, A and B. This period typically ranges from 200 to 400 milliseconds, and it depends on several factors. The first factor is the circuit breaker tripping time. It should be in the range of 40 to 100 milliseconds, and this time period depends on the efficiency and performance of the device. The newer it is, the shorter the tripping time will be. The second factor that it depends on is, you can find the average time. The reset time for the relay is typically between 40 to 70 milliseconds. As we mentioned before, nothing happens in a time frame of 0. When a fault occurs, the relay needs some time to activate the pickup. If the fault is cleared, it also requires time to return to its normal state. The reset time is the time the relay needs to return to its normal state after the voltage is removed or after the pickup is cleared. The third factor we need to consider is the error in time measurement, which ranges from 50 to 100 milliseconds. There are no limits from 50 to 100 milliseconds, and there are no limits from 50 to 100 milliseconds. The fourth factor is the safety margin, which ranges from 30 to 100 milliseconds and is denoted by the symbol TS or T margin. So the four factors that this time gap or relay time grading margin depends on are the first factor. The second and third factors, along with the fourth, show that practical experience suggests the optimal value for relay coordination is 200 to 400 milliseconds between stages. For instance, if the first stage trips at 1 second, the second should trip at 1.2, 1.3, or 1.4 seconds. The aim of this time grading is to ensure correct discrimination between stages. Ignoring this in overcurrent setting calculations risks a 1% chance of two relays operating for the same fault, complicating fault location identification, and potentially causing unnecessary supply loss. While fixed values are often used, the best approach is to calculate based on relay location or technology. Grading margins differ for electromechanical, numerical, static, and digital relays. Similarly, oil circuit breaker retrieving time differs from SF6 circuit breaker to prevent coordination failures. There is a 1% chance that two different relays in the same location will operate for the same fault. This leads to difficulties in distinguishing the fault locations, especially in cases where there is unnecessary loss of supply. Practically, it is common to use fixed values in all cases. However, the best and most accurate approach is to calculate them each time based on the relay location or the relay technology used. We cannot consider the grading margin values for both electromechanical relays and numerical relays to be the same. The same applies to static relays or digital relays. At the same time, we cannot assume that the oil circuit breaker retrieving time is the same as that of an SF6 circuit breaker to avoid failures in time coordination. To coordinate between different relays, the following steps must be followed, which are essential for conducting any study. The first step is to carry out a detailed study of short circuit calculations in the network. This can be done manually in small networks or using ready-made software in larger networks. From this study, we can expect the maximum and minimum short circuit current that is expected to pass through the bus bar. The second step is to conduct a study to determine the value that will pass through each branch in the network. Then, in the third step, we define the time interval between each two consecutive stages, which we mentioned ranges from 2 seconds to 4 seconds. It shows 2 seconds until it shows 4 seconds. It shows 2 seconds until it shows 4. The renaissance of a nation